what page? Sorry, what page is section 7 points? What page is Patrick?
That's going to be page 518.
Page 518. Okay, page 518. We're on page 518 and diagonalization. So understand what we mean by similar matrices, diagonalize a matrix, and find powers as matrices. You'll see why we want to diagonalize a matrix. So, like I say, let's take another example. We did this in Cayley-Hamilton. Now, say if you had a matrix like 1, 2, 3, 4, you want to find a to the power 100. Okay, you could use Cayley-Hamilton. You could say Cayley-Hamilton. There's only one problem with Cayley-Hamilton. What can you think of? What might be a problem with Cayley-Hamilton? It's good. I mean, it's better than trying to, a times a times a. Cayley is much better. Good, more algebra, less arithmetic. Yep. That might be more of an error that you'll get anyway. I mean, can you think of anything else? How did we work out A4? What did we need?
To keep squaring.
Yeah, you have to have a lower. You have to have a lower power, didn't it, to use that? Okay. We want to see if we can get direct to a to the 100. We don't want to work out, say we want a to the 100, you want to work out a squared, then a to the 4, then a to the 6, then a to the 7, or whatever, a to the 99, and then work out a to the 100. We don't want to do that. Sure, you don't want to do that. Okay, a to the 4, a to the 10 you can do with Cayley-Hamilton, but a to the 100 definitely not. You want to go directly from a to the 100. That's what you want. Okay, this is why I think softwares tend to use this diagonalization method to find a to the 100. This is what they use. What does diagonalization mean? So Cayley has got advantages, but it's also got a great, significant drawback in the sense that you've got to work out the earlier powers, the smaller powers, before you work out a to the 100, which we don't want to do. Okay, and what we do here, when we diagonalize, is we break a matrix A. Any matrix which is given to you, you break it down into, you factorize into 3 matrices. Of course, you might argue, why should I get one matrix into 3? There's a good reason why you want to break a matrix down into 3 matrices. Because one of those matrices will be a diagonal matrix. What is a diagonal matrix? What is a diagonal matrix? Sorry? Yeah, exactly. So a diagonal matrix is something like D. Let's call it D. A diagonal matrix. Hang on, let me write it down. Diagonal matrix is something like D is equal to, I don't know, 1, 0, 0, 2 or something. That's a diagonal matrix, okay? That's an example of a diagonal matrix. Of course, you might say, what advantage is there of a diagonal matrix? First thing, let's take hang on. Let me write a 3 by 3. Let's say I've got a diagonal matrix. D is equal to 1, 0, 0, 0, 2, 0, 0, 0, 3. That's a good matrix, okay? And we're going to use that. We're going to convert the geometry A to something like this. Now, the great advantage of a diagonal matrix is what? First thing is, go on then, Patrick.
It's easier to find the determinant.
It's easier to find the determinant. Not just that, but what's the inverse of that matrix? What's the inverse of this matrix? It's so easy. If I ask you what's D minus 1, you should be able to tell me what it is without working it out. Yeah, 1, yeah. 1, go ahead. A half, yes. And third, yeah. And 0 is everywhere else, isn't it? Okay, that's what it's going to be, isn't it? Okay. The inverse is given by that, isn't it? Okay, because 1 times 1 is going to give you, all you want is D times D minus 1 got to give you 1 along the leading diagonal, doesn't it? Okay, so inverse of our diagonal matrix is easy. And guess what else? Guess what D to the 100 is? If I ask you D to the 100, guess what that's going to be? I'm going to show you later what it is, but I'll tell you, I'll sort of spoil the show a bit. I'll tell you why diagonal matrix is so much better. Sorry? Yeah, 1, yeah. Yeah, 2 to the 100, yep. And 3 to the 100. That's what it is. That's why you want a diagonal matrix. So if you're working out a to the 100, you don't work out you do work out a to the 100, but you shift the problem to working that one out. That's what you shift it to. You shift it from A, you transfer it to something like this. So because this one is easy. The D to 100 of that, if I ask you to do D to 100, it's quite easy, straightforward. 1 to the power 100, 2, whatever the diagonal entries are, raise them to the power 100 or a million, whatever it may be. So you transfer the problem into, a diagonal matrix. Diagonal is easy to deal with. To find the inverse is easy, okay, and also to find the powers of a diagonal matrix is easy. What does this diagonalization mean? What it means is this, okay, is that you're given a matrix, an n by n matrix, like that, okay, like that n by n matrix, okay, and you convert it into a diagonal matrix, okay, you convert that into a diagonal matrix. That's what diagonalization is, and that process is called diagonalization. I know in the book I could use Z for, because I think the publisher were OUP, and they wanted to sell to the American market, but in the notes I students say, well, why are you writing S for when you've got Z in the book? I go, well, that's for this is for the domestic market, and that's for the international market. Okay, what has this got to do with eigenvalues, eigenvectors? Why is this placed, diagonalization placed in chapter 7? Why is it chapter 1? Why are we waiting to do 7 chapters? And I said, okay, hang on, why didn't I do this in chapter 1? We did what do you call it? We multiplied matrices, okay? We added matrices. Why didn't I do this earlier? It's definitely because it's got everything to do with eigenvalues, eigenvectors. Guess what those values are going to be? Guess what they're going to be? Those entries, those entries on the leading diagonal. They're going to be the eigenvalues of the matrix. These are going to be the eigenvalues. That's why you've got to wait until now. Okay, when did we find these? Okay. Anyway, let's go back a bit now. Let's develop the whole theory. So what we want to do is to what do you call it? Develop this theory of diagonalization, and the advantage we'll have to come to on Tuesday when we meet next Tuesday. Okay, so let's show if you're given A and you work out P minus 1 AP, okay, P minus 1 AP, you can do this in your own time. You'll find that P minus 1 AP is equal to you know how to deal with 2 by 2 matrices. You get 2, 0, 0, 1. That's what you get, yeah? If you work it out, the multiplication, I'm sorry, you can't see. This is what you get, okay? That's what P minus 1 AP is equal to. We say a square matrix B is similar. Let me zoom out a bit. It's similar to matrix A, okay? B is similar to A, okay? If there is a matrix P, inverted matrix P, such that P minus 1 AP is equal to B. So we say they're similar matrices. I'll tell you what that means in a second. They've got a lot of things which are more or less the same. One, the determinant is the same for a start, okay? So we say B is similar to A if you can find. So, in this case, the example we just did, A was, what was A equal to? A was equal to, I forgot what A was. A was 1, 1, 0, 1, 0, 1, 2. So, for example, this matrix, A, is similar to this matrix here, okay? That matrix, this matrix here, the one which is given to us, A, is similar to that matrix there, okay? If you've got this, if you've got an inverse matrix, P minus AP, you can derive it, then we say they are similar matrices. Well, what sort of properties does it have? Well, first thing is, it's called what's called an equivalence relation. So if you've got A is similar to A, clearly, okay? It's reflexive, okay? And symmetric. If A is similar to B, then B is similar to A, okay? That's called a symmetric property. And then you've got a transitive property, which says that if A is similar to B and B is similar to C, then A is similar to C, yeah? Okay, the last one is if A is similar to B, B is similar to C, then A is similar to C. Okay, one thing we want to show. What are these? One thing we want to say, if let A and B be similar matrices, the eigenvalues are the same. If A and B are similar matrices, we're going to have the same eigenvalues. Now, how do I show that if A and B are similar matrices, then they've got the same eigenvalue? That's good, because that will well, first thing, that means they were the same determinant, okay, because the determinant of a matrix is given by the product of the eigenvalues. So how do we prove this? What do you want to prove? What do you want to prove? Okay, if I say A and B are similar, what does that mean? We are given A and B Yeah, Patrick, go
I'm
on.
just thinking, does that mean that they're nearly the same?
Well, yeah, there's certain properties, but yeah. I mean, the word similar in English means something different in mathematics, as clearly as you.
Yeah, I know.
Okay.
That was all I noticed,
Yeah, but one thing we know is that what this is saying, it's got the same eigenvalues. It's got the same eigenvalues. That's good. You know, like I say, for a start, you know, the determinant is the same then, for a start. Okay, so we've given that A and B are similar, and we want to show it's got the same eigenvalue. We want to show this for any matrix, not just the one particular one, for any one. Okay, so if A and B are similar, what does that mean? Look at the definition. That means you've got this. Okay, that means there's an invertible matrix P minus 1 AP is equal to B, doesn't it? Okay, if they're similar, A and B are similar, you must have an invertible matrix. So we have, by definition, we have you know, P minus 1 AP is equal to B, haven't we? Yeah. Now, what do we want to show? What do we need to show? Come on, what do you want to show? The proposition says show that if they're similar, they've got the same eigenvalues. How do you find the eigenvalues of a matrix? How do you find the eigenvalues of a matrix? Come on. How would you? Go on, Patrick.
Well, you need to put like A minus
lambda I,
lambda
yeah?
I, yeah.
And determinant, yeah? Okay. You want to show, we're required to prove, we want to show this, don't you? Would you agree? We want to show required to prove that the determinant of B minus lambda I is the same as the determinant of A minus lambda I. Do you agree? That's what we want to show. If we can show that, if we show the same equation, yeah, for A and B, then it's going to have the same solution, isn't it? Yeah. So how do we show this? Look at the left-hand side. Consider the left-hand side. So we got determinant of B minus lambda I. What? Okay. What can we do with this? Yep.
Maybe B with B with A.
Well, not B with A, but B is equal to this, isn't it? Yeah. B is equal to this. Okay, we're told B is equal to this. So we can say this is the determinant of P minus 1 AP minus lambda I. Yeah? We can write that, can't we? Yeah? Because B is equal to P minus 1 AP. That's what I've substituted. Okay? I can do that. What about lambda I? What's I equal to? Think of it in terms of P minus 1P. Would you agree with this? P minus 1 AP.
Can't say.
That's not the answer I'm looking for, Patrick. I asked you, what can we replace I with? You say I can't see. Doesn't make sense. What can you replace I with?
1 0 0 1.
Yeah, no, something else. I want to use P's. Yep. Yeah, of course. I can replace P minus 1P, couldn't I? I could do that, can't I? Do you agree? Because the inverse times P, okay? Now, what can I do with this? Now, why would you say what? Lambda is a number, is a scalar, okay? What can you do with this?
Can you swap the minus P with the lambda or something?
No, well, you could do that, yes. You could put the lambda wherever you want in there, yeah. Yeah, take the P minus 1P out. Take the left P minus 1. Remember, you've got to be careful when you do matrix multiplication. Remember, order matters, doesn't it? Yeah, okay. From the left-hand side, you take P minus 1 out, okay. Right-hand side, take out P, can't you? Yeah? Okay, so we can write this as the determinant of P minus 1, okay? Yeah? A, okay, minus lambda I P. Do you agree with that? Do you agree with that? Okay. P minus 1A, I've taken from the left-hand side, I've taken the P minus 1 out, yeah? On the right-hand side, I've taken the P out.
Yeah. Okay.
Now, what about determinant of X times Y times Z? What's that equal to? The property that we proved, well, we might not have proved it, but I definitely stated it. What's the determinant of X times Y times Z? What can you do with this? Yeah, you can take the determinant in, like you can take the determinant in like the square root, yeah, okay? Determinant, this is determinant of p minus 1 times the determinant, times the determinant of a minus lambda I times the determinant of p. Okay? Now, we want to show, look at our destination. We're nearly there. We want to show determinant of b minus lambda I is equal to determinant of a minus lambda I. I've got that on the left-hand side. And how do I get this on the right side? I've got it there. Go ahead.
Well, could you swap maybe the determinant of p around?
You can swap it around anyway because now we're dealing with numbers. We're dealing with scalars, aren't we? Yeah. You can definitely write this as determinant of p minus 1 times determinant of p times the determinant of a minus lambda I. You could definitely do that. What do you think this determinant is going to equal? You know this one. Oh yeah, determinant of I. What's determinant of I? Sorry? Well, it's 1, isn't it?
Yeah.
Okay, the determinant of I is 1. So this is equal to 1. That is equal to 1. And so you end up by saying this is equal to the determinant of a minus lambda I. So you've shown that determinant of, b minus lambda I is determinant of a minus lambda I. And that's your proof. Okay? So you've got the same equation. That means if A and B are similar, you've definitely got the same eigenvalues. Do you got the same equation? Okay? You've got the same equation if they're similar. Okay, now what we want to do is introduced to diagonalization is we want to show an n by n matrix A. We say it's diagonalizable diagonalizable if it's similar to a diagonal matrix D. You can diagonal a matrix A if you can find it's similar to a diagonal matrix D. Okay, so you've got to what you've got to do is find an inverted matrix P minus 1 AP gives you a diagonal matrix. That's what you want. Can we diagonalize that matrix? Can we do that? Well, we've already done it. Guess where we did this? Guess where we did it? The first example we did. Look, I told you this was the matrix A. Okay, that was the matrix A. Let me zoom into that. That was the matrix A. That was, I told you, multiply by this, and you got that, didn't you? And that is definitely a diagonal matrix. Not because I call it D, but because it's got zeros off the leading diagonal. Okay, so can we diagonalize a matrix? Okay, and we've already diagonalized one matrix. The first, that's why I picked on that example. So we say, we can convert a matrix A into a diagonal matrix by left multiplying by P minus 1 and right multiplying by P. Okay, left multiplying by P minus 1 and right multiplying. Well, of course, then you might say, where do I get this matrix P from? Where the hell does the matrix P come from? There's got to be ways of. And why do we do this? Is like I said, is when you want to work out, when you want to work out d to the power 100, it's easy. Much easier to do d to the power 100 than a to the power 100. But like I say, we'll show they're equal anyway. All right. How do we show that this matrix, you can diagonal this matrix? 3, 0, 0, 2. How would you diagonal this matrix? Sorry? It's already a diagonal matrix. So what's going to be your P? It's going to be I, isn't it? Yeah? Your P, your invertible matrix. You need to find a matrix. Of course, it's going to be I. This is already a diagonal matrix, isn't it? That's your diagonalize. It's already a diagonal matrix. Okay, so trivial. And your P, in this case, your P is going to be I, isn't it? Clearly. P is going to be I, yeah? And so if you do P minus 1, if you do P minus 1, A, P, of course, you'll get the same matrix A, don't you? Which is already a diagonal matrix anyway. It was already, it was already a diagonal matrix. Okay, but just before we finish, how do we know which matrix we can diagonalize? Which matrix can we diagonalize? How would you know that? Well, one of the conditions is it's got to have, it's got to have, if you've got n by n matrix, okay, it's got to have n linearly independent eigenvectors. If you can get if you've got n by n matrix, if you have n linearly independent eigenvectors, then you can diagonalize the matrix. If you haven't, you can't diagonalize it. So there's no point just going blindly on autopilot trying to diagonalize a matrix when you might not be able to. First, you've got to check, have you got, for an n by n, so for a 4 by 4 matrix, you've got to make sure you've got 4 linearly independent eigenvectors. If you've got that, you can diagonalize that matrix. Okay? and I'll tell you how you do this when we meet on Tuesday. Any questions?
I just wonder,